Good morning, champs. Today we determine the internal forces in a cantilever beam carrying a linearly varying distributed load. The beam is 4 meters long. The load intensity is 0 at the wall and increases linearly until it reaches 6 kilonewtons per meter at the free end. We measure X from the wall toward the free end. Before making the cut, we need to choose which side of the beam to isolate. If we keep the right-hand segment, the included distributed load has a trapezoidal shape. If we keep the left-hand segment, the included load is triangular. The triangular load is easier to replace with an equivalent force, so we keep the left-hand segment. The disadvantage is that the left segment contains the fixed support, which means we must calculate the support reactions first. The entire distributed load forms a triangle. Its equivalent force equals 1/2 times the maximum load intensity times the beam length. 1/2 times 6 times 4 gives 12 kilonewtons. This force acts 2/3 of the beam length from the zero load side, which is 2.67 meters from the wall. Horizontal equilibrium gives a horizontal support reaction of 0. Vertical equilibrium gives a vertical reaction of 12 kilonewtons upward. Moment equilibrium about the wall gives a counterclockwise support moment of 32 kilonewton meters. Now we make a cut at position X and keep the left-hand segment. For this course, our positive directions on the left cut face are axial force to the right, shear force downward, and bending moment counterclockwise. Other conventions are possible, but every arrow and equilibrium equation must remain consistent with the convention chosen. The load intensity at the cut depends on X. Because the load varies linearly, we use similar triangles. The load intensity at the cut equals the maximum load intensity divided by the total beam length multiplied by X. 6 divided by 4 gives 1.5, so the load intensity at the cut is 1.5 times kilonewtons per meter. The distributed load included on the left segment forms a triangle. Its equivalent force equals 1/2 times its base times its height. The base is X, and the height is 1.5x. Therefore, the equivalent force equals 0.75x squared kilonewtons. This equivalent force acts at the centroid of the triangular load. Since the larger side is located at the cut, the force acts 1/3 of x from the cut, or 2/3 of x from the wall. We begin with horizontal equilibrium. There are no horizontal external loads, so the axial force is 0 everywhere. Next, we determine the shear force. The vertical support reaction acts upward. The triangular load resultant and our assumed positive shear force both act downward. Vertical equilibrium therefore gives the shear force equal to the support reaction minus the equivalent distributed load force. The shear force function is 12 minus 0.75x squared kilonewtons. At the wall, where x is 0, the shear force is 12 kilonewtons. At the free end, where x is 4 meters, the shear force becomes 0. Now we determine the bending moment. We take moments about the cut and define counterclockwise as positive. The internal bending moment and the fixed support moment are counterclockwise. The vertical support reaction produces a clockwise moment about the cut. The equivalent distributed load force acts to the left of the cut and produces a counterclockwise moment. The resulting bending moment function is negative 32 plus 12, x minus 0.25x cubed kilonewton meters. At the wall, where x is 0, the bending moment is negative 32 kilonewton meters. At the free end, where x is 4 meters, the bending moment becomes 0. Notice the pattern. A linearly varying distributed load produces a quadratic shear force function and a cubic bending moment function. With our coordinate direction and sign convention, the rate of change of shear equals the negative distributed load. The rate of change of bending moment equals the shear force. Therefore, the second derivative of bending moment equals the negative distributed load. The most important lesson is not that we must always keep the left side. The lesson is that we should choose the side of the cut that creates the simpler free body diagram. In this problem, choosing the left segment gives us a triangle instead of a trapezoid, which makes the equivalent force calculation much easier.